Yeah,
So it says give the expression for the normalized wave function that is shown over here. So what is shown over here is actually the real part of the wave function, because the wave function is a complex function. There's a real and an imaginary part. The real part is something we can just draw. So that's basically what is given over here. Now, for a particle in the ring, the general form of the wave function will be something like this. So, if it is a function of just phi, then we have some normalization factor, n, and then we know it has the form e plus minus I ml phi. That is the most general form for a particle on a ring. So this is not the final answer that this question is trying to extract from us, because we have more information. For instance, we can actually see how many swings it makes. Okay, so if we look at this function here, this complex exponent, the real part of that is, so I'm going to write this out as the real part of this function. That is n times cosine ml phi. Right, so it is something that swings as a function of phi. Now, phi is, of course, the angle in that ring, right? And I see that it actually looks like a cosine function as a function of phi. I can actually count how many swings it makes, right? Let's do that, because that's what you want to do in this particular question. So let's start over here. This over here is one swing. One. This is two. This is three, 4, and 5. 5 swings. What does that mean? Well, it means that this ml equals 5. What is it, plus or minus? I don't know. I don't know if it's plus or minus, but I can tell you that this function here is going to be 5 phi. Okay? That's why this question is kind of nice, because there's a visual representation of what this ml does. ml adds the number of waves that you fit onto a ring. Can you fit 1 wave, 2 waves, 3, 4, in terms of the swings, the number of swings it makes. It makes 5 swings here, and therefore this ml equals 5. So this function then I can write as follows. The normalization factor, maybe you remember this. We have done this normalization factor several times for this situation. And the normalization factor is 2 pi r, where r is the radius of the ring. It's called r0, just to be clear that it's not a variable, it's a constant. And then the function is e to the power plus minus I ml is now 5 phi. So that is the most information I can get from this wave function. Yes? This is the real part of the complex exponential function, right? So if I have a complex exponential function, I to the power, e to the I power, e to the power ix, that is cosine x plus I sine x. So that's what I'm using there. I'm only showing the real part, this, which is the cosine. Okay. Second question, compute the angular momentum of this particle. Okay, so what do? You want to compute the angular momentum. Let's do the complete thing. So I want to operate on this wave function with this operator, LZ, on this function, and see what I get. Well, let's write it as this, in this one. Fine. No, let's do it in this one. So, what is this LZ operator? Well, that's basically a derivative with respect to phi. That is the form of this operator. And the wave function is this normalization factor, which is not so important now, so just write n. And I have plus minus I 5 phi. So I have to take the derivative of that function. So that is going to be, take the derivative of this complex exponent, which is not so difficult to do, because what I get is plus minus I 5. That factor is still there. And then I get the function again, right? So I can just write this. Yes?
So the angular momentum is the same as the projection for this? Isn't LZ the projection?
Yeah, in this case, that's good. I mean, this question is ill-phrased, I would say. It's not a good question for the exam. What is intended here is the projection of the angular momentum. But since this is a particle on a ring, this is pretty much the same. Because it's not really a three-dimensional problem. Okay? So your angular momentum here is the projection on the z-axis. It's the only angular momentum that there is. That's why it holds here. But in general, yeah, you're right. If this would be a particle on a ring on a sphere, then we would have to be more precise about what we mean. So this is going to be plus minus h bar times 5, or in other words, 5 times h bar times function again. So the eigenvalue here of this operator is plus or minus 5 h bar. Now this is something you can certainly do. Alternatively, for this particular question, I can also do the following. I can do, write this function, which we have done several times, simply in terms of this. This is the only quantum number that matters. So I can write it in terms of a ket. And in this case, that will be just 5. Okay? So there's one way to write a function, and then I can operate on it with my operator. And we have seen this relation a lot, because basically the answer here is just simply ml h bar times the function again. Since ml is 5, it's right here. Okay? I should be doing plus minus 5 because we don't know the sign, so let's put that to be more complete. Same answer. So but I'm using here this general relation LZ operating on a function ML is always going to be ML H bar ML. That is the eigenvalue equation. Written very shortly. Now you can do both ways. You can certainly, if you know this, you can do it really quick. If you feel more comfortable with taking a derivative of a function to make sure that you're doing the right thing, I invite you to do that. Either way is fine. All right. Question C says, what is the energy associated with this circular motion? Or what is the energy eigenvalue of this wave function? But we don't have to do a whole computation here. We can actually go to the last page of the exam, and it says actually there the on the ring is a function of ml, which would be ml squared, h bar squared, divided by 2i. I, of course, is the moment of inertia on a ring. Is here, and ml is my quantum number, h bar, of course, h bar. So I have everything I need to know here. Let's write out this capital I, because capital I is something I can also compute, because it's equal to m, which is the mass of the electron, times r squared. Sorry, this is a very funky E, sorry, it's not an L, this is E, this is the mass of the electron. So, if I'm asked to compute this, then I have to actually calculate this, not just write it, and I have to fill out all these values. I know everything. This is 5, this h bar is given, mass of the electron is given, r is given in the question as well. It's 1 angstrom. So I can just fill out all those numbers and just literally calculate what the energy is. (1.52 times 10 to the negative 17 joules. That's what comes out of this. Don't forget to square the ml, okay? 5 squared is 25. So it's not 5 times h bar squared, it's 25. This is just filling out a formula, which is given on the exam, the last page, okay? All right, last question for this problem. It's about the probability density of the electron on the ring. Question is, based on the probability distribution of the electron, identify the number of nodes along the ring. How many nodes? This is kind of like, it's not a hard question, but it's kind of a tricky question, especially when you are staring at this thing. Because you're inclined to count the number of times it crosses 0. Right? Or not? What do you think? You don't know, right? So, what we want to do, we want to write down the actual probability density. What's the probability? What's the probability? Density is a function. Sorry. Modulus squared. That's the probability density. That is the probability of finding the particle in this really tiny segment of the angle, dphi. Very tiny position right there on the ring. What is the chance of finding electron? It's given by this whole expression. It's called probability density. Now, what is this? Actually, I should be more precise. It's actually R0 dphi. Okay? Because the size of the ring depends on R0. So I can fill this out because I have an expression for the wave function. Okay, the normalization factor was this, R0. But I'm going to square this thing, so this square root is going to go away. Okay, so it's 1 over 2 pi R0. I can multiply by R0 on top here. That's good, so that disappears. R0 is divided out. And then, it is the wave, it's basically the complex exponent times its complex conjugate equals 1. So that's 1 and then times dphi. So what this thing is just 1 over 2 pi dphi. What does that mean? That means that for every position, every tiny little spot on this circle with a width of dv anywhere in the ring, there's a chance of finding the particle that is 1 over 2 pi. We've seen this before. In other words, There are no nodes. Okay? The concentration of electrons on a ring here is uniform. It's in equal sense anywhere along the ring.